Okay, let's give you guys some practice. So determine if this alternating series will converge or if it will diverge. So press pause and have a go. Okay, so to do this, we need to make sure that all three conditions are satisfied. So we should check this. We should check that the limit of un as n tends to infinity will head towards 0. So looking at this, we need to look at un. We need to look at our un, meaning we need to isolate this. We only want to extract the un. So looking at this, we need to isolate this. We need to isolate this. So ignore this and just look at the un. So just extract the un. So when looking at this whole thing here, we should just consider 4n over n squared plus 25. So this here is our un. This here is our un. This is our un. So make sure that the limit as n tends to infinity will be 0. So as n tends to infinity, the numerator will just act as 4n. The denominator, as n tends to infinity, as n gets bigger and bigger, you're adding a 25. This 25 here is going to be negligible as n tends to infinity. So the denominator will just act as n squared. So now this whole thing here will just act as 4 over n. So when you take the limit as n tends to infinity, this whole thing here will head towards 0. So as n tends to infinity, this whole thing here will head towards 0, meaning as n tends to infinity, the whole thing will head towards 0. So this will be satisfied. Now we need to check this one here. So in the domain from 1 to infinity, will all our uns be positive? Will all our uns be positive? So looking at this, in the domain from 1 to infinity, this will always be positive. Therefore, the whole denominator will always be positive. While looking at the numerator, from 1 to infinity, the numerator will be positive. So the denominator is positive, numerator positive, therefore the whole thing will always be positive. So this has been satisfied. So now we need to check that it's non-increasing, meaning make sure the next term will always be less than or equal to our current term. So two ways of doing this. One way is to replace all the n's with n plus 1. That's one way. So this would be n plus 1, and then this would be n plus 1 squared. Okay, that's one way. Or the other way is to map a function. So one way is to do as replace all the n's with n plus 1. The other way would be to map a function on top of this thing here and make sure that the derivative is always negative or equals to 0. So this is one way of doing it. The other way is doing it this way. So we are going to take this route. So looking at the un, we can map our function. So this is our un here. This is our un here. So now we can map a function on top of this. So we can map a function on top of this. So looking at the un here, you could do this. You could do this. You can map a function on top of our sequence here. So map a function on top of it. So that would then give us this plus 25. We could do this, or we could write it as this. So these two are pretty. We are mapping a function on top of our sequence. This is also a function. So we are entitled to write it in this form. We could write it as this, 4x over n. They're both functions. So this is valid. This is also valid. Okay. Sometimes it's written like this. Sometimes it's written like this. But they're both valid. They're both functions. So now we want to make sure that our function is always decreasing or staying the same. So now we need to differentiate this. So look at f prime. So differentiate this. Use the quotient rule. That will then give you this. Tidy this up. That will then give you this. So now we need to ask when will our function be negative? Meaning when will this be negative? So looking at this, this will be positive. Will always be positive. So now when would this be negative? Because we want to know when f prime will be negative. So when would this thing be negative? It would be negative when this thing is less than 0. So now add this to both sides. That will then give us this, and then divide both sides by 4. That will then give us this. It would be negative when n is greater or equal to 5. Well, precisely speaking, it will be non-increasing when n is bigger or equal to 5. Okay, so looking at this, we want to look at this, but then this will only be satisfied when n is 5 or above. So we need to truncate this series and only look at it from 5 onwards, because there's a rule that says that you can truncate it, and if you're testing for convergence, these two will be the same thing. So we can just truncate this and just look at the tail end of the series. Well, looking at this, this will be satisfied. This will be satisfied. But by the way, looking at this, this will be satisfied. This will be satisfied, but this will not be satisfied. It will only be satisfied when you look at 5 onwards. So we would truncate this and just look at the tail end of things. So now looking at this, this will be satisfied. This will be satisfied. This will be satisfied. Therefore, the whole thing here. Therefore, this thing will converge. Well, there's a theorem that says if you look at the tail end of things, this will also be satisfied as well. So you are allowed to cut it. So here let's say you got from 1 and then this here is 5. If you just look at the tail end, if the tail end converge, therefore the whole thing here will converge. Meaning this thing here will converge, therefore this thing here will converge. Okay.